Hello, everybody, and welcome to Acceleration Due to Gravity. This is our last lesson from the kinematics unit. And my last video of the day. I've made all of the kinematics videos in one day, and I'm getting pretty tired. So let's finish this one off strong. So we've done most of the kinematics stuff to this point, or all the content that we're going to cover. We are going to look at one more special case. So we're not going to learn any new formulas or any new processes, but we are going to look at acceleration due to gravity. So up until this point, I think we've only been looking at problems where acceleration is due to, like, stepping on the gas pedal in a car or something like that. But there is an acceleration due to gravity. So any problem where something is falling or being thrown into the air is subject to gravity, which, hopefully makes sense. So ignoring air friction. So this is something we're going to do for the entire course, is we're not going to deal with air friction, but ignoring air friction, all objects accelerate towards the Earth at the same rate. So when you drop a bowling ball or a feather, and drop a bowling ball and a feather, they are going to accelerate towards the ground at the same acceleration. The difference, obviously, is air friction, right? The bowling ball is going to have a lot less air friction than the feather. So in real life, they wouldn't fall at the same rate. But this experiment's been done on the moon, which doesn't have an atmosphere, and they drop the bowling ball and the feather, and they hit the ground at the exact same time. It's actually on YouTube. Super grainy video. Obviously, it happened a long time ago, but really cool to watch nonetheless. And that acceleration, so this acceleration towards Earth is a consistent number. It's a constant number, and that acceleration is 9.8 meters per second squared. So that's how things fast towards the Earth. That's how fast things accelerate towards the Earth. Just be careful, because normally we make downward negative in a lot of problems. So in that case, acceleration is negative 9.8, and it's 9.81 actually. We might as well be exact. 9.81 meters per second. So depending on which way you designate as a negative value and which way you designate as a positive value, you just have to be consistent. So your acceleration can be positive or negative. Most of the time, people say downwards negative, so that acceleration becomes negative 9.81 meters per second squared. So let's do a problem. A student drops their homework into a well. After 2.4 seconds, it hits the water at the bottom. How deep is the well? So this is something falling, acceleration due to gravity. So if we are to write all the things that we know, well, we already know acceleration is negative 9.8 meters per second squared. So this is probably a good time to draw a picture. We have a person, and they're going to drop something down this well, and we got to figure out how deep the well is, or the distance. We know acceleration is downwards. So there's a couple different ways you can approach this problem. You can say downward direction is negative, upward direction is positive. That's kind of how we've been doing it this entire time. And if you want to stick with that, then definitely stick with that. Sometimes, I'm just going to redraw this. Sometimes when everything is happening in one direction, for example, in this example, they're dropping their homework into the well, so everything's happening downwards. It does make the math a little bit easier to make the direction that you're moving the positive direction, and then the other way would be the opposite, would be the negative direction, because the whole problem is happening in one direction, right? The homework is falling downwards. There's nothing else happening. So if you make downwards positive, as long as you stay consistent, you're going to get the same answer no matter what. So if you feel comfortable with that, do that. If not, we'll stick with making downward negative and upward positive. So our acceleration acts downwards, therefore acceleration will be negative, which I've put right there. Okay, that's my little spiel on you set the direction, just be consistent with it. What else do we know about this? Well, we know the time. It took the homework 2.4 seconds to hit the bottom. And that seems to be it. So there is a bit of a trick here because you're dropping your homework. So at that moment that you drop it or let it go, that very split second, right when you let it go, your initial velocity is 0, right? You let it go, its initial velocity is 0, it starts to accelerate downward, and the velocity starts to increase in a downward direction. So this is kind of the one that throws people off, is when you drop something, the initial velocity is 0. So there's a few little tricks. And we're trying to, we're not trying to find velocity final. We don't know velocity final. I apologize. We're trying to find displacement. Okay, so we have acceleration, we have time, we have v initial, and we need to find d. Well, we can use, if we look at our formula sheet, we can use v initial multiplied by time plus 1/2 a t squared. Right, that has all the things we need. We don't even need to isolate a variable, so that's perfect. So d is equal to 0 multiplied by 4.25. This formula is really nice for anything starting at rest, because that whole first term is going to disappear. Plus 1/2 negative 9.81 Why I'm writing 4.25? That's from a different question. I apologize. 2.4 seconds. Oh man, maybe 6 videos in one day is too many videos. 2.4 seconds squared. Don't forget that squared. So this whole thing disappears. It's multiplied by 0. Anything multiplied by 0 goes away. So we just need to calculate this part. And when we do that, we're going to get negative 28 meters. I can see in this answer key that they're being weird about sig fig. So let's do that calculation on our own, just in case, so that it's exact. So it is negative 28.224 meters. I don't mind if you round to negative 28 meters. Either way, I will know that you're right. So yeah, so now we found out that the well is 28 meters deep. Hopefully that makes sense. Let's do a couple more. I've got a few more examples in this one because there are a few tricks, and it's important that I show you some of these tricks. So example 2, a football is kicked straight up into the air at 15 meters per second. How high does it go, and what is its total hang time? And what hang time means is how long is it in the air for. So let's draw a picture. Let's get green out so we can have a football field. And then I don't think I have brown, so let's just use black. So a ball is kicked into the air. It's going to reach a high point, and then it's going to come back down all the way down. So what do we know? Well, we know that's being thrown into the air. So we know acceleration, negative 9.81 meters per second squared. I'll make downwards negative, upwards positive. We know that it's been kicked at, sorry, that's not final. Initially, it's kicked at 15 meters per second. That's basically all that we know. We are trying to find the displacement, or the height, right? How far does it travel? We don't know time. So we only know 2 pieces of information. We need to know another piece of information. So here, this is another trick with acceleration due to gravity problems. So let's think about this football for a second. The ball goes up into the air. So its velocity starts at 15 meters per second. And as it goes up, acceleration is downwards, right? So acceleration is working against that velocity. It's trying to pull that ball back to the earth. So that ball is going to start to slow down. So it's going to go up. It's going to start to slow down. It's going to hit a high point. And at that high point, it's going to turn around. So the velocity is going to go from going upwards to downwards. And there's a point when you change from a positive value to a negative value. What is the point in the middle of those? So like, even if you think of a number line, you have a point in the middle, you have 1, 2, 3, -1, -2. What's the point in the middle? What's between positive and negative? That's 0. So when your velocity is going upwards, we've said that's a positive direction, but after it hits the high point, it's going to turn around. The velocity is going to be negative. So there's a small instant right at the top of the flight path that the velocity is going to be 0. So what we can do is we can say, well, let's cut this problem in half. Let's not even worry about the last half. Let's just look at its path to the top, because we want to know the displacement to the top. So at the top, the velocity final is 0 meters per second. Hopefully that made sense. I might have over-explained it, but I tend to do that. So if we just look at the upward path of this football, at the very top of its path, the velocity final is 0, and now we have enough to solve this problem. We have v final, v initial, and acceleration, and we're looking for displacement. So what we can do is use our v final squared is equal to v initial squared plus 2ad. And we're looking for displacement, so let's do some formula manipulation. So the first thing I want to do is subtract vi squared from both sides, and that gives me v final squared minus v initial squared is equal to 2ad. So we just got rid of the term in front of it. Now I want to get rid of the 2 and the acceleration. So what I can do is divide by 2 and a to both sides. And you can see that what happens is I cancel on this side. So now I have, let me move this over a little bit further. Going to run out of room. Now my formula looks like this. D is equal to v final squared minus v initial squared over 2 times the acceleration. And I just need to plug in those values. So vf squared is 0 squared minus 15 squared all over 2 times negative 9.81. And I can calculate that. It's going to be negative 225 over negative 19.6. And we get a distance of positive 11 meters. So that football went 11 meters in the air before it started to come back down. All right, what is its total hang time? How long is it in the air for? So what you can do is, again, we are only going to look at the first half of this problem. You can think of this problem as the football goes up to the top, and then the football falls down back to the ground. There's like 2 halves of this problem. And because we're not dealing with air friction, the time to go up is going to equal the time to come down. So if we know the time to go up, we can just multiply it by 2 to get the total time. Hopefully that made sense. So we know the initial is 15. We know acceleration is negative 9.81. We know v final because we're just looking at the first half of the problem. So v final is going to be 0 meters per second. And we know displacement now is 11 meters, and we're looking for time. So in this case, we can use v final is equal to v initial plus a t, and we can solve for t. So I will subtract v naught from both sides, or v initial, sorry. I keep using inconsistent language, I apologize. So what happens now is I've got v final minus v initial. These ones cancel out, is equal to AT, and then I can divide by A to both sides. And I'm left with T is equal to v final minus v initial over acceleration. And I just need to plug those values in. 0 minus 15 all over acceleration, which is negative 9.81. And you can see that we get a time of 1.53 seconds. But that's just the time it takes for the football to travel all the way to the top. And we want to multiply that by 2 to get the time that it goes all the way to the top and all the way back down. So that will give us a time of 3.1 seconds. Fantastic. Okay, one more practice problem, or one more example problem here. A little bit trickier, but again, I need to show you all of these things. A student stands on the edge of a 45-meter high cliff. They throw their physics homework straight up at 12 meters per second. So what we're going to assume in this problem is we have this cliff. It's 45 meters tall. The homework is getting thrown straight up, and then it's going to hit some high point, and it's going to fall all the way down to the bottom of the cliff. So it says, how long does it take to come back down to the same height as the student? This is a bit of a tricky problem because, well, we're dealing with something thrown in the air. So we know acceleration is going to be negative 9.8 meters per second. We know initial velocity is 12 meters per second. We're trying to find time, and we don't know anything else. There's a couple of different ways you can approach this. You can ignore everything that happens below and do this very similar to the problem we just did with the football. Find the time it takes to get to its high point and multiply that by 2, knowing that the high point is going to have a velocity of 0. But one thing that you need to know about projectile motion or things being thrown is the speed. Let's zoom in a little bit. The speed of the homework at this height, moving upwards, positive 12 meters per second, is going to be the same speed as the homework now moving downwards at the same height, but in the opposite direction. So that's negative 12 meters per second. So when the homework, I drew it as a ball, I apologize. When the homework goes up and then comes back down at the same height, it's going to be going the exact same speed, but in the opposite direction. So if you were to throw something, we're not going to do two-dimensional motion, but let's imagine kicking. You kick a ball. That's a foot. You kick a ball, and it goes up in a pattern like that. Well, the speed that the ball is moving here is going to be the same speed that the ball is moving at the same height, but on the opposite side. So if it's moving up at positive 10 meters a second, at the same height, it's going to be moving down at negative 10 meters per second. If the ball was here and it was traveling at positive 13 meters per second, well, at the same height, but on the other side, it's going to be traveling at negative 13 meters per second. And that's just because we don't have air friction. Normally, if we had air friction, it would be a little bit different, but in this case, we're not dealing with air friction. So with that in mind, we can say that if we ignore everything after the, if we make this part of the question, when the ball is at the same height on its way down, as our final, just because we only worry about the time to that point, then we can say the V final is equal to negative 12 meters per second. And now we have VF, VI, A, and T. So we can use VF is equal to V naught, VI, sorry, I keep writing V naught, VI plus A, T. And we can solve for T. So we'll subtract VI from both sides. And we'll divide by a from both sides, so that we have t is equal to Vf minus Vi over a, and we can just plug that in to be negative 12 meters per second minus 12 meters per second, all over negative 9.81 meters per second squared. And negative 12 minus 12 is negative 24. And that gives us a time of 2.45 seconds. Awesome. So now it says if it falls all the way to the bottom of the cliff, how fast is it traveling when it hits the ground? So in this case, we know, if I look back at my really awesome picture, we know in the yellow highlighted area, the velocity of the homework going downwards at that point is 12 meters per second. And if it travels from that point all the way to the bottom of the cliff, it's going to go negative 45 meters. Because this is, we're assuming like this is height 0 and this is height negative 45, if that makes sense. So using this knowledge, we know that the distance, or the displacement here, is going to be negative 45 meters. The initial velocity, so we're going to take the yellow highlighted portion of this question to be our initial part. It doesn't really matter what happened before that, because at this part we know it's moving at negative 12 meters per second. And we know the acceleration is going to be negative 9.81 meters per second squared because it's falling, so it's subject to gravity. And we are looking for how fast is it traveling when it hits the ground. We are looking for the final velocity. So if we have Vf, or if we're looking for Vf, we have A, Vi, and D, we can use V final squared is equal to V initial squared plus 2AD. We don't even have to do formula manipulation because Vf is mostly isolated. We'll have to do one step at the end. So Vi is negative 12 squared plus 2 times negative 9.81 times negative 45. And we know that we will get 144 plus 882. And we get a V final squared of 1026. Be really careful here. We still have squared, Vf squared. We're not done yet. We have to square root both sides, and that will give us a V final of 32 meters per second. So that's how fast the homework is traveling at the bottom. Okay, I did explain those quite a bit, but hopefully as you move into these problems, things will make a lot more sense. I apologize for the longer video. Some of them will be longer, some of them will be shorter. But I'm going to stop rambling now so you can go to bed. Talk to you all later.